Good morning. We have 9 minutes of morning left. I just got here from the United States yesterday, so I'm not really fully convinced that it is even morning. I don't know what time of day it is, but I'm happy to be here and glad that you're here. So we're going to talk about Cassandra and Spark today. I'm going to give you a rough idea of the architecture of Cassandra, the data model of Cassandra, the architecture of Spark, and kind of the basic programming model of Spark. And I will write some code also. I'll show you an example of what a very simple analytic application in Spark, in Scala, looks like. So that's kind of the flow for this talk. A little bit about me, then I want to ask you a little bit about you, and then we'll get started. So I am from the United States. I live in Denver, which is kind of in the middle or western third of the country. And I work for a company called DataStax. We're a company whose business is Cassandra. So that particular database, that's what we do. My job is I'm the director of training, which means that all of the curriculum that we make that teaches people how things like this work, my team builds that stuff. We make a bunch of videos and put those online for free. I might mention those videos again in this talk. It's possible that I will mention a website called DataStax Academy, which is a site that my team makes. And if you want like the 5-hour version of this, if you want to see me talking about Spark and Cassandra for 5 hours, that's a lot of me. You're already getting like an hour and a half of me at the conference today. That's a lot. But if you want more, you can get that online. So there you go. Now, you, questions about you. Anybody using Cassandra in production right now? Dude, like a third of you. I love you. Okay, so forgive me when I introduce you to Cassandra. You guys already know that, but the rest of you may not. Anybody using Spark in production right now? Okay, you guys are amazing. All right, there were the different thirds, as far as I can tell. Not many of you. Anybody doing both? Okay, all right, one. You could be totally bored by this. I don't know. You probably already know everything I'm going to say. And if you, so you're leaving now, right? Okay. I didn't mean you had to leave, but you should know this is introductory for that interface. So good. All right, you're making the right choice. Because no, don't laugh at him. Love him. No, seriously, it's more important to me that you are in a room that you're interested in than that you're in my room, right? Because you have choices. Anyway, let's talk. Let's talk about Cassandra. Now, Cassandra is a distributed database. It is built from the ground up to be a distributed database, and it is a transactional database. So another big data system that has had a lot of attention is Hadoop, right? Hadoop is it's in part a distributed file system. So if you've got way too much data to put on one computer and you need lots of computers to store it, HDFS is a nice way to do that. HDFS is built for systems where the data doesn't change all that quickly. Cassandra is built for systems where it is built as a transactional database. So it works when you've got too much data to put in one place and the data is changing rapidly. That's important. If your data is relatively static, like you dump new logs in every night or something like that, Cassandra usually just doesn't work out. The economics don't work out. But if you know your data's changing a lot, you got a lot of data, low latency, single-digit millisecond reads and writes, that's when you use Cassandra. So again, too much data that changes a lot, a system that's always on. These are the kinds of requirements people think of when they deploy Cassandra. If you have a small data problem, if you have data that fits easily on one server, and like one Postgres server gets the job done, do that. That's way easier. Like if you have small text files, you want to count the words in small text files. I have a command here called WC that works amazingly well for that. So again, we're talking about problems that are too big for one machine. That's key. I want to tell you a little bit about the Cassandra data model and its architecture as a distributed system, because those are good things to know as you're getting to know the database, and they have consequences that lead us to want a tool like Spark. Cassandra is very good at some things, kind of bad at some things, and mixing the two, adding Spark to Cassandra, makes a lot of sense, and you don't know why until you see how the data model works. So let me walk you through it, and we'll see what's going on. Now, this is an actual table, and this is the Cassandra query language, or CQL. I like to just call it SQL, because I'm a troll. And it looks a lot like SQL. The data model is tabular, just like a relational database. So you kind of walk into the room and look at this, and you're like, wow, it looks really familiar, and that's good. But it's also bad, right? Because it's not quite relational. It'll, in some cases, trick you. So you need to be careful here. By the way, as I'm talking about this, if you guys have questions, please put your hand up and we'll talk about them now rather than do them at the end, because they'll always make more sense now. So just interrupt me, put your hand up, if you've got a question, I'll most likely call you. All right, so here's the data model, or here's an example table of credit card transactions. It's pretty easy to get an idea of what the fields are, but let's talk about the key, the primary key. That's a weird thing in Cassandra. And a lot of attention goes into primary key design, more so than in relational databases. So, that first column in the key, that's called the partition key, all right? The partition key is going to help the database know what server to put this row on. And I'll show you some more pictures of that in a minute, so just keep that in your head. That second guy, or that's the partition key, the first column in the primary key. That second one is called a clustering column, all right? That's called a clustering column. And that's gonna provide some ordering of rows inside a partition. I'll show you a picture in just a minute. So together, those are the primary key, those two columns. But it's not like a compound primary key in a relational database. When people do this in relational databases, it makes me mad. I don't like compound primary keys. Maybe it's just a stylistic thing, but you have to do this in Cassandra very often. So check it out. Here's that same data as a table, that same schema with some actual data in it. And there's our partition key, and there's our clustering column. The two of them together are a primary key. So the two of them together are going to uniquely identify a row. Now, a partition is the collection of rows that have the same partition key. So many rows, potentially even tens of thousands of rows, can have the same partition key. So there's another partition, there's another partition, it's lonely, it only has one row, but that's fine. That works perfectly fine. Those are partitions. Now partitions are always guaranteed to be stored on the same node. And that's a good thing. That way we've got all that data that's local, and we can do interesting things in a performant way with those rows inside a partition. Let me show you what I mean by that. So here is a row. That's a credit card number, and the time the transaction took place, and the amount of the transaction in US dollars. And so what we're going to do is we're going to take that partition key, that's the credit card number, and run it through some hash function, doesn't really matter what, we're just going to hash it, and come up with a number. Now, this ring here represents a Cassandra database. This is an 8-node Cassandra cluster. All the nodes are perfectly identical. They're all peers. There's no leader, there's no master, there's no primary, there's no nothing, right? All of them are peers, except each one of them gets a unique token. You see those numbers on there in hexadecimal. The real tokens are 64 bits long in an actual Cassandra cluster. This is a special 16-bit, like Arduino version of Cassandra. Plus, the numbers fit on the slide better. You don't want to see, nobody wants to see real tokens, ever. So, we hash that partition key, we get a number, and that's going to tell us, that's going to be, let's see, it's bigger than 4,000, less than 6,000, so that row will get written to the node with the token 6,000. That's one of the primary problems we have to solve. If we've got a distributed database and you want to write something to it, where in the database do you write it? And that's how we do this. This is a technique called consistent hashing. Now, this is a very simple overview. We could literally talk for hours about all of the complexities that happen when you do something like this. Like, I'm not talking about replication, I'm not talking about consistency. Those are all things that Cassandra solves in really cool ways. But basically, I just want you to know this much. Good so far? All right. Back to this table here. Now let's look at that partition. Notice because it's a partition, they have to have the same value of the partition key, but the clustering keys are different. Is that highlighting show notice? There you go, okay. The clustering keys have different values. Inside of a partition, rows are ordered by clustering keys. Notice it's 159 and then 203. They'll always be ordered. They're ordered on disk. They come back ordered. We can do range queries of partition keys and have all kinds of fun like that. You can never do a range query of a partition key, though. Why is that? Here's a question for you. Thinking back to the slide before and the way things get distributed, why couldn't I do a range key?
You actually can do if you do it with single key. What was it? By card number.
If I had the.
If you have both parts of the key, you can do that.
Yeah, but if I can't do a range query just by card number, like all the cards between 6,000 and 7,000.
You cannot do it because of the different nodes.
Yes.
And you have to join it somehow.
Because of the hash function. The partition key gets hashed, and on the backside of a hash function, I don't have ordering anymore. I do have ordering inside a partition, and that's good. So a lot of Cassandra data modeling involves playing with clustering keys and designing tables so that they have the right key to be able to satisfy my queries quickly and efficiently. So what you find that you do is you design tables to satisfy queries. You don't do that in the relational world. In the relational world, you design tables around entities. In Cassandra, you do some entity modeling, but then you combine that with the queries that your application is going to run, and you build tables to answer queries. All right? What are some consequences of this? Let's jump ahead here. Consequences of this data model. Oh, question. And microphone for you.
Yeah, not all types support ordering. Is there any limitations on the clustering key?
Yeah, are there some types of clustering keys that cannot be ordered? For example, if not all types support ordering that makes any sense. Clustering keys are always going to be ordered because of the way the storage engine works on disk. It will apply an ordering to them, and they will be stored there. But like, if you had a UUID as a clustering key, and you can have a UUID as a clustering key, the ordering doesn't mean anything, right? It's ordered. Wait, what? There we are, okay. It is ordered, and they will be in a predictable order. It doesn't, you don't care. But it basically, on disk, something implements comparable and it gets the job done, whether it means anything or not. And just briefly there, it's not unusual to throw a UUID in on the end of a primary key in a Cassandra table, just to give you uniqueness. You're not really thinking about ordering anymore there. But things like integers, strings, time UUIDs, those are types that commonly show up in clustering keys, where the ordering is semantically meaningful. Sir? What? I don't know, I think your hand was first. I say so.
Thanks. Do we have any opportunity to manage your partitioning? I mean, you have a hash function, which is a quite closed box, and actually we don't know on which node each piece of data will be stored. And because of that, we cannot perform some action on the node we want. If we start a query, it involves all of the cluster to compute the data.
Right. So, in purely Cassandra.
Yeah, I understand that this hash function allows you to split the data in the equal pieces or something like that, to avoid putting all data on the same node. But on the other side, we cannot
put our computation where we want it.
Exactly.
Yeah, so in purely Cassandra terms, you don't care. And Cassandra makes it so you don't care. When you're doing computation on the data, you do care where the data goes. And that really is a Spark Cassandra integration question. So this being an introductory talk, I don't talk about the details there, but I will say when you've got data from Cassandra and data from some other place, then there's some optimization you can do in your Spark job to make sure that you've got the data in the same place. It's not difficult, but it can be done. And I'd say it's part of the work. Question there.
Can I have composable transaction, partition key or the other type of a key?
Partition and clustering.
Clustering key, right. Can I have like composed of string and data?
If I understand the question correctly, yes, you can have a user-defined type, so you can create UDTs or user-defined types in Cassandra, and a user-defined type can participate in a clustering key.
So I just can have my key defined of tuple, but I can define user type, and it will store both string and data.
Yes. Also, you can have more than one clustering key, if that's a simpler answer to your question. So I can have as many columns as I want there in the clustering key. All right. All right, got a question up here. I did say, ask questions, didn't I? You guys are not disappointing me.
Can you please explain in the old terms, in talking about compact storage, what means primary key? So clustering key is the column name or it's something else?
The clustering key is...
So there
It's a
was
column.
row key and column name previously in compact storage.
I don't understand. Ask again.
The previous versions of Cassandra had another way of I'm talking about thrift protocol and
Got it. Okay, thrift. And you're saying, can I explain clustering key in terms of thrift?
yes.
No. I mean, not right now. That would take too long, but afterward, if you want to talk about that, yes. The way I very much understand the question, and it's cool how it works. I just can't go into it yet. So let's talk after.
Let's talk about it.
Yes. All right. No more hands. Moving on. So, consequences of the data model. It's amazing if you want very fast reads and writes based on queries that you know. Again, when as a developer you're building a Cassandra data model, you build the model with queries in mind. We've got a course on DataStax Academy that's, again, like 5 hours of videos. It's not me this time, it's somebody else. It's okay, it's still good. And part of the process is do your entity model, your conceptual model, and then list your queries. And then with those two, you create a data model. So as long as you know your questions, know your queries, it's great. That's what it's built for. However, if you have ad hoc queries that you're trying to do, it doesn't work quite as well. It's difficult to do ad hoc analysis inside Cassandra. Difficult to do aggregation. I forgot to mention this. Up until recently in Cassandra, secondary indexes, that is, say I have a key with username as the partition key, and I've got email address somewhere else in the table. Until recently, it has not worked well at all to index email and to be able to do a query based on that. You get your primary key and that's it. You don't get to build other indices. Pretty limited, right? Now, there's reasons why it has to be limiting, because it's a distributed database. And these consequences of the data model make it so that you can build a very fast, very big database, but there are some kinds of things you can't do with it. And that's why we have Spark. We would want to integrate Spark with Cassandra to solve that problem. So, when would you use Spark? You don't have to use Spark with Cassandra. You can use it on top of flat files. You can use it with HDFS. You can use it with stuff in S3. Spark doesn't really care where your data is stored. But, again, you need to have too much data to put in one place. Now, you know how when people like me show you distributed computing frameworks, there's one demo everybody does. What's that demo? Word count. I am not going to do word count today. My commitment. Thank you. Yeah, I'm kind of tired of it myself. There is like one line of code in this thing where I count things and it feels like word count, but it's not. Anyway, yeah, if you have word count for a novel, it fits on your computer. And like I said, use WC, please. It's very effective. It's incredibly fast. But if you've got petabytes of stuff to count, you need to distribute that problem. So Spark is for that. Spark also works well for ad hoc analysis, if you don't know the questions ahead of time. Spark has a SQL, what do you call it, mode, where you can execute SQL queries over data in Spark. So if you've got ad hoc things to do, it works great. And let's just say you're tired of MapReduce or you're tired of Hadoop. So guys, as a developer, to me, the big difference here is, the big difference with Spark is that it is so much more pleasant to use. It feels like writing code. And when I get to the code in a few minutes, it looks like I'm just writing code. I mean, it's not, MapReduce was so awful. Have you ever actually implemented the map and reduce interfaces in Hadoop? Has anybody ever really done that? It doesn't, a few of you. It doesn't happen much because it hurts. And so what the Hadoop ecosystem did is it created all of these other tools on top of that. So very few people ever really do that. You use some higher level API. And that's good because those were not pleasant. Spark, I honestly think the reason why Spark is seeing adoption and creating the excitement that it's creating isn't just because it's a little bit faster. It is a little faster, but I think it's because it's easier for people like us to use. It feels more like writing programs. And we like to write programs, last time I checked. All right, I'm going to tell you a little bit about the data model, if you could call it that, a little bit about the architecture, and then I'll do a demo. And was it lunchtime after that? We'll find out. Okay. Now, the data model in Spark is a moving target. There are at least 3 models kind of in play right now in the Spark world. The most basic and oldest is called the RDD. RDD stands for Resilient Distributed Data Set. Now, RDDs will eventually be obsolete. They're going to be replaced with a thing called data sets, which are a lot like RDDs, but we're going to play with RDDs today because they're easy to understand, and at least in the Java and Scala Spark worlds, they're still pretty universal. A lot of people are using them. So, an RDD is storage agnostic. Spark doesn't care where it lives. When I do the demo, I'm going to create an RDD from a Cassandra table, obviously, and a CSV. So that's a legitimate place to get one from. You can also read data in HDFS and various other connectors. It doesn't care, it just comes from somewhere. An RDD is fundamentally a big bucket of records. So that's the only data model that really has to be true of an RDD. It's not just bytes, undifferentiated bytes, but it has things in it. You can think of it in that sense like a text file. A text file has that structure. A text file has lines, and an RDD has records. So that's as far as it goes. The type, those records are typed, but they can be simply strings, they can be tuples, they can be typed tuples, and I'll show you both kinds. When you read from a Cassandra table, by default, you get an RDD full of objects called Cassandra row. I think we made that up ourselves. It's a good name. So yeah, they're just a big bucket of things, and they're fundamentally distributed, which means they will be partitioned among multiple nodes in the Spark cluster. Fair warning, the Spark cluster and the Cassandra cluster that you're going to see me running, they're both located right here. It's a one-node cluster. It's pretty exciting. But, hey, you'll be able to see what I do. RDDs are immutable. They're these collections of records that are typed, and they are immutable. So when I create one, by reading from a Cassandra table, I can never change that RDD. Of course, I will want to change it, but in the world of computing that uses immutable things, we transform one immutable thing into another immutable thing. And that's one of the kinds of things that I'll do to an RDD, is I will call a method on it. The RDD is an object, by the way, in the Scala REPL I'll be using. It just looks like an object. I'll call a method on it. That's a transformation method. That transformation will return a new RDD. And then I can transform that RDD and transform that. I can split them and do all kinds of things. I can just make RDDs into other RDDs. And in effect, really, I'm creating this graph, this directed acyclic graph of computations. And that's when I'm writing a Spark application, that's really what I'm doing, is I'm telling the Spark cluster manager, hey, or the client, hey, here's the graph of my stuff. Take that graph and evaluate it later on. Because I have a directed acyclic graph of these immutable objects, then we get to do cool things like lazily evaluate that graph. And eventually, when I ask for some computation with an action, which is another method I can call on the RDD object, then Spark will say, oh, okay, let me walk back through the graph and see what parts of your computation I actually need to realize, and maybe what parts of the computation I already have laying around because you did them earlier and you were smart and you asked me to cache them in RAM. That's a key optimization step. And when you do this, when you build a non-trivial application in Spark, you probably will want to draw out the graph explicitly and look and say, oh, hey, maybe I did this thing here that caused a partitioning that I didn't need to do. Let me undo that. Or I had this step, and if I cache that step, if I persist it, I won't have to repeat that computation later on. So optimizing a Spark application requires you to think about what that graph looks like and be smart about when you reuse parts of it. The code I write today is not advanced enough to do that with. In fact, okay, those of you who are using Spark already, don't do this during the demo, but after, when we're done. If you can tell me, it's suboptimal. I partitioned twice when I should only partition once. So see if you can find out where that is and tell me later. And tell me why I wrote it that way. That's an exercise for the advanced Spark student. Now, we don't have time, we've got lots of time. I said this is like it's better than MapReduce. I said that. I mean, I didn't say those words, but I implied it strongly. Watch me, okay, don't let me get away with this here, because then I said there's two things you do to RDDs. There's transformations and actions. And action is kind of like do some computation on these transforms. Does that sound familiar to anybody? Yeah, so it's not MapReduce. It is a better API, but MapReduce is there kind of winking at you from behind the curtain the whole time. In fact, there is a transformation, I'll call it, called map, and there's an action called reduce. So it's still there. The basic idea that we've got distributed data in our Cassandra cluster, and we want to move the computation to where the data is, so we'll scatter the computation and then gather the results back to one place. That idea is still there. And I mean, I don't think we'll ever get away from that as long as we're building distributed systems this way. So it's not so fundamentally different. It's just that the API we get to use, again, feels a little more native if you're used to writing code. Now, I think that's enough of slides. And the right thing to do next would be code. Do you agree? I've never had anyone say no to that. No, Tim, we want more slides. We love your Spark image, Tim. We'd just like to see more of that. Yes, it's great, but probably code is better. All right, let's take a, oh, hey, I should create a Spark shell. Font size, everybody, this isn't too deep of a room. Is that okay? Can you see all right?
Yeah.
Okay. I am of an age where I like glasses on for seeing text, and so I understand if you would also like that. Let's run a Spark shell, and I want to show you the schema that we're going to play with. Excellent. The primary entry point here to our application is an object called the Spark context. When I run this shell, this is a Scala REPL that's got a few objects created for me. It's a Scala REPL that's got Spark behind it. I automatically have an instance of the Spark context. And I'm for purposes of convenience, I'm running the community version of DataStax Enterprise. All of this stuff is possible as open source. The connector, Spark is Apache, an Apache project. Cassandra is an Apache project. The Spark Cassandra connector is open source, so you do not need a commercial product to do this. I happen to be running one because I'm a loyal company man, and it's super easy. I type DSC Spark and it happens. So, I'm not selling anything. It's not there. You know what? I am selling DataStax Academy. That's the thing. Academy.datastax.com. I'll say it again. Go watch free videos there and learn this stuff better. Now, let's show you my schema. Here's what I'm going to do. We have. Seriously? Okay. Movies. All of the DataStax curriculum that you will see, hopefully ever, uses kind of a fictional company. All of the stories that we tell inside our curriculum take place inside this startup called Killer Video. And it's kind of like a YouTube clone that does some things slightly differently. So we've got all these movie-based examples. My talk later tonight, I'll also be talking about film. I guess it's a thing for me. But notice the schema. All that stuff at the bottom where it says with Bloom filter, FP chance, and all that down below, forget about that. That's just default, so you don't care right now. What you care about is these three columns. Movie ID, release year, and title. That's our movie database here. And I think I have, in this example data set, really super big data. There's no way you could ever do this with a relational database. I think I have about 170 films or something like that. Absolutely mind-blowing load. Another question, just to make sure you're in the game here. Why on earth would I use a UUID?
Because it will allow you to partition it quite well if your hash function is quite simple with this.
It'll allow me to partition well if I have a hash function. Really anything, if I hash it though, technically, as long as my hash function isn't stupid, I can hash anything and it should distribute.
It's unique and it's not ordered.
It's unique and it's not ordered, was the answer, yes. And more to the point, it's not ordered because I can't order. Right? If it's MySQL, I can make a primary key auto-incrementing. If it's Oracle, hopefully it's not, but if it is, if it's Oracle, I can make a sequence and I can use that for my next ID, right? There's nowhere I can go for the next thing because any of the nodes might be doing the right. So there is, in a distributed system, next is a fuzzy concept, like now is a fuzzy concept. We just don't have access to things like that. So I have to use a UUID, as unpleasant as they are to look at. And by the way, in a real Cassandra table in production, if you did this, you'd get fired. It's nice. It's absolutely terrible. So those are ugly. You got to look at those on the screen, but we have to use them. We have to use them because it's a distributed database. And I have here title from movies, a small collection of films to play around with. Also, let's see what else I have here. Let me kill that, and I've got this. Oh, question.
So why don't you use a clustering key? And
Oh no, yeah, okay. So stop there. The data model is for the real world terrible. It's a good data model for a demo though. There's and this happens to us all the time. You know, when you're trying to teach a principle about a thing, sometimes you have to make things up a little bit so that the principle is very clear, and you can use that principle to solve a real problem out in the world. I probably wouldn't really use this data model in reality, but it's very clear for showing things like this. So, right, I would design the schema differently in the real site. I have this CSV file here. It's got, this is designed for people with small heads. I'm not that guy, okay? It hurts a little bit. We're almost done, it's okay. CSV file, I've got movie IDs and ratings. So imagine that this is like some app that they have. You go to the movie theater and you can rate the movie in real time while you're watching it. But I get the movie ID, I don't know what that is. So I'd like to convert that into a name, And I would like to average those ratings. You can see just by looking at the UUIDs that the same movie is rated multiple times. So what we want to do is average these and then join that to the Cassandra table. So I'm joining a CSV file to a Cassandra table, things which ought not to be done, ever. Let's go ahead and run the Spark shell and make that happen. I'll just give you a quick idea of what basic Spark code looks like in Scala. Now, we are pair programming starting right now. So if you see me make a silly mistake, just shout it out. It'll go faster. If you call me out, that's what pair programming is all about. Let's do it. I'm going to start by reading in that ratings file, and we'll use the text file method on the Spark context. And I will, let's see, that's users, TL Berglund, workshops, Spark. I call that file movie ratings. Just read that in. Now, these are lazily evaluated, of course. I could have gotten the file name wrong, and I wouldn't even know yet. So let me, yeah, that's sweet. So when I do things like that, that's when you call me out. There you go. I forced it to actually go read the file in and return the first record of the RDD. And what is the type of records in that RDD? You are hired. Who said that? Okay, excellent. But who cares about that? I can't really work with that. I need to do some things to it. We'll get there in a minute. Let's read in my movies. I will use the Cassandra table method. Again, we name all these methods ourselves. And that is in the killer video key space. Key space is just a container of tables, and it's the movies table. Now, if I just read that in, and I get a Cassandra row RDD full of these records called Cassandra rows. And if you don't mind, if you'll just permit me, I'm gonna take a little bit more time than that and map things here. So let's see. Anytime you see an ID, I'll call that ID, that's a string, and a year, that's an int, and a title, that's a string. Anytime I see a tuple with those types, I am going to return a tuple. Right there, that's the Scala literal for a tuple. And what I want that to be is an actual UUID, so Java util.uuid from string. So I'm going to parse that string ID and make it into an actual UUID, and then I'll just return the title as a string. Now, did our hero get things right? He did not. Pay no attention to that warning. Our hero did, in fact, get that right. So now we have a tuple that's a UUID and a string. Good news, okay? Pirates of the Caribbean was the first thing. So I've got this movies RDD, and I've got the ratings RDD. We need to do some work on the ratings RDD. But I want to point out something about the movies RDD that is special. It's special because it's a tuple that has two elements in it. And an RDD whose type is a size 2 tuple is called a pair RDD. And with pair RDDs, we get special methods that we like. We get extra APIs that work. For example, we get a method called, famously, boom, we get join. Yes. So if it's a pair RDD, I can join. And a pair RDD is assumed to be a key value pair where the first element is the key, the second element is the value. All right, and the value element can itself be a tuple. It can be whatever data type, but the first element is the key, and as long as the keys are joinable, then we're in good shape. So I need to get that movie ratings whipped into shape so that it's the right kind of thing. Let's do that. So I'm going to make, let's clear the screen here, ratings by ID, and that's going to start with ratings, and I'm going to call a method called, wait for it, yeah, map. All right, now map wants an anonymous function. So what map is going to do is it's going to go to every record in the source RDD, apply this function to it, create a new RDD with a record that is the return value of the function. You can probably guess what I'm going to do. let's see. So I've got a line, and I want to make fields, which will be line split on a comma. There you go. Now I've got an array of fields, and now I'm going to create a tuple. What's the value going to be? The value is going to be, that's the rating. And what's this going to be? Again, yeah? Good? Compiles. 197 ratings. Mind-blowing. Big data. Dare you to do that in awk. All right. What's it got in it? I like it. All right. I'm encouraged. I feel like we can do something with this. The UUIDs are the same key. I could join these, but we're not really there. I want average ratings, and I don't have average ratings yet. So I could join ratings to movie, and then I'd have the title and the rating, but it's all this data, and nobody would care. You wouldn't be impressed. So what I want to do is I want an RDD, a pair RDD of average ratings, where the key is my movie ID, and the value is an average rating. To get that, I need to sum the ratings, and I need to count the ratings, and I need to group the ratings by key. Because you saw in the CSV file that there were lots of ratings with a common key. So what I want to do is I want to go to this ratings by RDD, group them up by key, and then do things with them. Let's go ahead and do that. So val rating count. No, that's too hard. I want to do rating sum. This is a little easier to see. Ratings by ID, and I want to group them by key and then apply a reducing function to them. And that I do. This API is just so hard to understand. I call a method called reduce by key. I love it. Now, this is going to do two things in once. It's going to go to the RDD, find all the common keys, group them, and then give me a new kind of like temporary intermediate RDD that's got the key and then a collection of all the ratings. And then it'll apply the reducing function to that collection, and that reducing function will be in Scala, because Scala is such a clear language, add the two things. What did I misspell? Yeah, okay. You guys were looking at that for like 30 seconds. You're like, oh, just wait, he's going to do it. Okay. Collect is a method that takes that result out in the cluster and brings it back to the client and shows it to me here. So that is the sum of the ratings. There are only 5 movies rated in there. So let's make now a rating count. This is the closest. The code I'm about to write here feels like word count code. Told you I'm not doing word count. I'm not doing word count. It just happens to, that the pattern shows up here. So let's see. Ratings by ID. No. I need to map the values. All right, map values is a transformation that's going to take every record in this pair RDD and apply a mapping function just to the value. So I'm going to get a new RDD that's got the same number of records, all the same keys, but a different value. So for this, and the way you count things in a distributed system is you go to all the things and you count them. So, okay, I see this thing, 1. Stick it over there. Like, oh, here's the next thing, 1. Stick it over there, right? So you just count each one and stick a 1 next to it, and then you gather them up later and you figure out how many 1s you had. That's kind of the functional distributed way of counting things. So let's do that. There we are. I'm going to map the values, and instead of a rating, I'm going to make every one a 1, and then I can reduce that by key with that same add all the things, and rating count, collect for each. So collect means bring the collection back, and then I've got that as a Scala collection, and I can call for each on it, and I pass the print line function to for each. So there we are. Hey, this is promising. We are almost there. I've got counts, I've got sums,
Now I have average ratings, and what am I going to do? I'm going to take my rating count and I'm going to join them to rating sums. Have I made a typo? No, I haven't. Okay. We're going to join those two things because they have the same key, and that works like a boss. Then I will map those values. I've got a rating, which is going to be a tuple. So the joined thing is going to be the value of the first RDD, comma, the value of the second RDD. So that's going to be count and then value, or sum, rather. And if I want the average, I will take the second member of that tuple and divide it by the first member of that tuple. You love Scala, don't deny it. Rating. Good? Nope, not. Map values. We got this. Oh boy, almost. Now, average ratings, join, movies, collect, for each, print line. And this pretty much gets us there. Now, it's still a little messy. We would want to map the values again and, or actually pull the value out of there and probably turn that into a new pair RDD. But for purposes of our demo and given the time, we can see. Now, what do all 5 of those films have in common? Does anybody see it? They're all Johnny Depp movies. Like, I don't even know why. I literally don't know why this happened. The people who make the data, they work for me, the sample data, and I don't know why these are all Johnny Depp movies. But I think their ratings are honest. The Tourist, widely underrated movie. Okay, it's really a good one. Everybody hated on it. Libertine, not really. So anyway, I think basically truthful ratings, and what we did was we took data in a Cassandra table and joined it to data, not just raw data in a CSV, but we did some primitive analysis on that CSV data and joined that to the Cassandra data. So this is a very basic example of what you can do with Spark and Cassandra. There is much, much more to say in terms of the details of the connector and optimization and other transformations and other actions and the rest of that whole world. And like I said, just to shamelessly plug, totally free videos you can see online, academy.datastax.com. Go there and check it out. 5 hours of me talking about Spark. Do it a little bit at a time, because that's a lot of Tim, I think, for anybody. So I'll hang around here for more questions afterward. Thank you very much for being here. I think we're at time, right? So should we?
One of the main concepts in Hadoop is to move your code to your data. How it works with Spark and Cassandra?
Exactly the same way. So the Spark Cassandra.
So command functions is executed on nodes where data in Cassandra collector?
Yes, Spark. The Spark code is executed. Spark runs on the Cassandra node as well. So that's always happening in the same place.